Hi there, welcome to another session of the Medication Mathematics course. Today we are going to focus our discussion on intravenous calculations. Intravenous medications are drugs that are administered through a vein. Intravenous therapy drugs may contain fluids such as saline, which is water with salt, dextrose, water with some sugar, vitamins, and electrolytes. It may also have other drug or chemical components, such as in the case of antibiotics or say thoraxine. There are some characteristics of IV routes and medications that we have to pay attention to. First, they are directly absorbed into the bloodstream and therefore they bypass the liver, which is also known as the first pass effect. They also have a rapid onset of action and therefore take effect immediately. So, with these characteristics, it becomes difficult for us to reverse its effects. And so IV medications are very potent and care should be taken when administering any medication through the vein. There are various forms of IV medications. First, we have intermittent bolus medications, which is signified by IVP, which is IV push. This involves smaller volumes of drugs administered over a few seconds to 30 minutes. They are administered mostly through a syringe. You'll find the time over which you should infuse or inject these medications in some common drug guides, such as your Davis Drug Guide or Nursing Central for nurses. We also have intermittent infusions signified by IV piggyback. This involves a moderate volume of diluent, usually saline or distilled water, such as in the case of antibiotics. Most of them have to be diluted before it can be infused. And they are administered over a period of about 30 minutes to 4 hours through a secondary infusion set. The last type is continuous IV infusion, which is signified by simply IV. This involves mostly large volumes administered over extended periods of time, normally 5 to 24 hours, using a primary infusion set. This may also be administered over several days. So for example, when you are dehydrated and you get to the hospital, you'll be given normal saline, which is an isotonic fluid. And this is just going to expand your blood volume. It may take several hours to a few days before your electrolytes are normalized. The objectives of this module is first for you to be able to describe and differentiate between primary and secondary administration of intravenous infusions. Identify abbreviations used for IV fluids. So we've talked about IVP, which is IV push for injectable medications. Then we have IVPB, which is IV piggyback, which is for intermittent infusions that are moderate in volume, such as your antibiotics. Then we have the IV, which signifies IV continuous infusions, which is for large volumes. You should also be able to identify the calibration in GTT per mil, which is also known as the drop factor. So when you pick an IV set, you should be able to identify the drop factor that has been printed on the IV set. Then calculate the flow rate using any of these methods, the ratio and proportion formula or dimensional analysis methods. Then recalculate flow rate to correct off-schedule infusions. So if you have a time and a volume, or a time and a rate, you should be able to recalculate the volume and rate, vice versa. So let's talk about infusion sets. There are two main types of infusion sets. We have a primary infusion set and a secondary infusion set. The primary infusion set is used to infuse medication by either gravity or through a pump. When you are using IV sets for pumps or by gravity, you need two things to be able to calculate your flow rate. You need the total volume to be infused and then the total time for the infusion. If you are going to be doing gravity, which is the drop per minute, then you are going to need a third component, which is the drop factor. We have macro drip set, which is 10 to 20 drops per ml, and then you have the micro drip set, which is 60 drops per ml. A secondary IV set is very similar to primary set, but has a shorter tubing. So when you look at the pictogram on the right side of this presentation, you will see that in B, you have two IV sets, A and B. A is going to be your primary set, and B will be your secondary set. When using a secondary IV set to complete gravity infusions or even in the pump, always remember to hang the bag higher than the primary bag so that you'll have the flow from the secondary bag. Alright, now let's begin some calculation examples. We are going to start by calculating infusion rates in ml per hour. So our question states, a client has a prescription for 1000 ml of normal saline to be infused over 8 hours. Normal saline is an isotonic fluid used as a blood volume expander. At what rate should the nurse infuse this medication? Alright, so let's go through our 5 steps. Step 1, we have to determine the variables in the question. Remember we said when we are doing any IV infusion rate calculations, we need the volume and then the time. So the volume given in this question is 1000, and then the time for infusion is 8 hours. Then we have to determine the final required units, and we know that we need this in ml per hour. Step 3 is to set up our equation. So using the formula method, we said rate is equal to total volume over hours of infusion, which is V over T. And then we replace our formula with the actual quantity. So we have volume, which is 1000 mLs, and then over time, which is 8 hours. Simplify your equation by using common factors, and we'll see that 8 goes into itself one time and goes into 1125 times. And so our rate is going to be 125 ml per hour. And this is what we will program into our pump. Let's do another example using the same question, but a different method. Okay, so we still have to determine the variables in the question, which is our volume and time. And we have 1000 ml for our volume and 8 hours for our time. Then we have to determine the final required unit, which is ml per hour. So when we set up our track line for our dimensional analysis, we have to make sure that ml is on top and HR, which is hour, is at the bottom because that's the final units that we want. Okay, so we have 1000 ml on top and then 8 hours below. Reduce this calculation by using common factors, and we will see that 8 is a common factor of 8 and 1000, and 8 will go into 1125. So once again, we get 125 ml per hour. Okay. Now let's do some practice questions. A client has a prescription for Protonix 40 milligrams in 100 ml of normal saline to be infused over 15 minutes. At what rate should the nurse set up the pump? For A, ml per minute, and then ml per hour. Leave your answer in the 10th decimal place. Okay. So let's determine the variables in the question. We have a desired dose, which is 40 milligrams. And then we have a volume, which is 100 ml. And we have a time, which is 15 minutes. Which of these components do we need in our calculation? Remember, we are not calculating the dose we need. We are calculating the rate. And so we are going to look for the volume of the diluent, which is 100 ml of the normal saline. So that is what we are going to use. So we need just the volume and then the time. Using ratio and proportion, we will set up our ratio. So we know that we have 100 ml to be given over 15 minutes. Okay, this is going to be equal to x, or x over 1. And so we have 100 ml times 1 equals to 15 minutes times x. This can also be set up using the proportion. So we have 100 ml is to 15 minutes and x is to 1. And when we set up our equation, or ratio is going to be 100 ml times 1 is to 15x, or 15 times x. And if we want x, then we have to divide each side by 15, and x will be equal to 100 ml over 15 minutes, which is going to give us 6.666. This means, this bar right here means that the number is recurrent. So we're going to have 6.66, 6666 to whatever extent ml per minute. Now the question says that we should leave our answer in the 10th decimal place. So the 10th decimal place is just up to 1 decimal place. So one significant figure after the decimal. That is what we are going to leave our answer in. So to do this, we have to first find the number or significant figure after the decimal place. And so this is going to be 6 after the decimal place. Then if this number or figure is less than 5, we are just going to drop all the other figures after that figure. However, if it's greater than 5, then we are going to round it up. So as we can see, 6 is greater than 5. It means that we have to round it up to the next figure or number. And so we are going to round this up to 7. And Therefore, our final answer is going to be 6.7 milliliters per minute. That will be our final answer. Okay. The B part states that we should find the rate per hour. Okay, so we know that we have 6.6666 ml per minute. We also know that in every hour we have 60 minutes. Okay, so when we set up our proportion, we are going to have 6.666 ml times 60 minutes all over 1 minute times 1 hour. So if we cancel out, then this minute will cancel this minute. And now we are going to multiply 6.666 by 60, and we're going to get 400 ml per hour as our final answer. We can also do this another way. We can say that 60 minutes is equal to 1 hour, or is to 1 hour. This is equal to 15 minutes to x. So we are looking for the hours, which will be comparable to 15 minutes. That is x. So let's set up our equation. We are going to multiply the outer figures and then the inner figures. And so 60x is equal to 1 hour times 15 minutes. And to find x, we divide each side by 60 minutes. And we will get 1 hour times 15 minutes all over 60 minutes. And so minute will cancel minute. And what we have is 15 divided by 60. And our resulting answer will be hours. So we will have 0.25 hours. Then once we have our time in hours, we simply divide the volume over time to get our rate of ml per hour. So 100 divided by 0.25 is going to result in 400 ml per hour, which will be our rate in ml per hour. So as you can see, both methods are going to give us the same result. Okay. Let's do some other examples to see if we can use this process or method to reach our final answer. A client has a prescription for vancomycin 1000 milligrams over 3 hours. Vancomycin comes in a 250 ml bag. What should be the rate for vancomycin in ml per hour? Leave your answer to the nearest whole number. So, first of all, let's find the components or the variables in this question. We have our volume to be 250. So our volume is 250 ml. And then our time is 3 hours. We know that rate is equal to volume over time. Okay? And so all that we are going to do is swap this with the actual figures. And so we have 250 ml divided by 3 hours. And that is going to give us, let's punch that on our calculator, 250 divided by 3. That will give us 83 0.33, and this is also recurrent. Okay, but the question says that we should leave our answer to the nearest whole. So whole numbers do not have decimal places, and so we will just look at our decimal point and see if the figure after the decimal point is greater than 5, then we are going to round the number before the decimal point up, and if it's below 5, then we are just going to drop everything. So 3 is less than 5, and so we are going to drop everything after the decimal place, and our answer to the nearest whole number is going to be 83 ml per hour. This is going to be our answer. Let's do another example. A client has a prescription for 1,000 milligrams of ofemev in 100 ml saline to be infused over 20 minutes. Ofemev is liquid Tylenol that is used as a combination therapy for pain management. So it reduces inflammation and fever. At what rate should the nurse administer the dose? Calculate your answer to the 10th in ml per minute, and then also calculate your answer in ml per hour. Okay, so let's see what are the variables. So we have volume, which is equal to 100 ml. We have time, which is equal to 20 minutes. All right, so volume is equal to 100 ml, and then time is equal to 20 minutes. We know that rate is equal to volume over time. So this is going to be 100 ml over 20 minutes. So 0 will cancel 0, and 2 will go into 10 5 times. And so we have 5 ml per minute. Okay. Now, the question says that we should also find our answer in ml per hour. There are 3 ways we can do this. We can first find the time in hours and then divide our volume by the time, or we can set up a proportion. We know that 5 ml is going to be over 1 minute. So how many hours would that be? Well, we know that we have this, which is 5 ml per each 1 minute, but in every hour that we need, there is going to be 60 minutes in that hour. Okay, so this will be 1 hour. So we know per 1 minute, we need per 1 hour. And minute will cancel minute here. And so we will multiply 5 by 60. 5 6 is 30. And we'll just add the 0. So 30 plus the 0 here. And so this will be 300 ml per each hour, 1 hour. So our final rate is going to be 300 ml per hour. This will be our final answer. So this is our rate of ml per minute, and then this is our rate for ml per hour. Example 3. A client is receiving D5W at a rate of 125 ml per hour. How much fluid will she have received in 8 hours? Okay, so now we know the rate and the time that has passed after the infusion was started. We just need how much fluid has infused. Okay, and so first of all, always make sure you write your variables. So we have our rate, which is 125 ml per hour. And then we know our time, which is 8 hours. Which is 8 hours. What we don't know is the volume that has infused. Okay, so we know that our rate is equal to volume over time. Now, we need volume. And so, to do that, we can do it using the formula method and just using some fundamental arithmetic. So R is equal to V over T. Now we can multiply each side by T, and T will cancel T. So now we have T R is equal to V. And so our volume is going to be the rate times the time. So let's reverse this. Volume is equal to time times rate. And this is going to be 8 hours times 125 ml per hour. And so hour will cancel hour, and we will multiply 8 by 125. And that will give us 1,000. So this means that the patient or the client is going to receive the whole 1000 cc bag in 8 hours. That will be our final answer. We can also use dimensional analysis to solve this. The final answer we want is ml or milliliters. So let's do our tracks. Okay. And so we have 125 ml per hour, and we are going to infuse this, or we have been infusing this over 8 hours. And so what is at the top will cancel what is at the bottom, and 8 times 125 will still give us our 1000 ml, because that is what is left. How do we find the amount or the infusion time, or the amount of time that the medication is going to take to infuse? Well, we are going to use the same formula method that we have been using. So a client has an order for Zoxyn, which is an antibiotic made up of 2 types of antibiotics, or 2 different kinds of antibiotics. 50 ml at a time, or at a rate of 12.5 ml per hour. How many hours should the nurse expect the infusion to take? Okay, so let's write down. We have 50 ml and 12.5 as our rate. So our volume is equal to 50 ml. Our rate is 12.5 ml per hour. Okay, using the formula method, we know that our rate is equal to volume over time. Now we need the time. Okay, so let's start by first multiplying each side by time. So time will cancel time over here. And now we have T, R, or time times rate, is equal to volume. So to find time, so time times rate is equal to volume, we have to divide each side by the rate. So rate will cancel rate on this side, and now we have time is equal to volume divided by the rate. Okay, let's put in our actual figures. So we have 50 ml divided by 12.5 ml over 1 hour, because that is per hour. And remember that we said anytime you have three divisions or three-tier divisions, the bottom one becomes a multiplication because it goes up. Okay, so we are going to have 50 ml divided by 12.5 ml times 1 hour. So ml will cancel ml, and now our final answer is going to be 50 divided by 12.5, 4. So it's going to take 4 hours for us to infuse 50 ml of Zoxyn at a rate of 12.5. So let us review. You can just use these simple methods to do your calculations if you remember these. To calculate the rate, you always have to divide the total volume by the total time for infusion. To convert from milliliters per minute to ml per hour, all you have to do is multiply your rate in ml per minute by 60. So 60 is going to be the common factor. To convert from ml per hour to ml per minute, just divide the rate in ml per hour by 60. Find the time for infusion, divide the volume by the rate. And then to find the total volume infused or amount infused, you multiply the time of infusion by the rate. So this will help you to do any calculations that involve your rate in ml per hour or ml per minute. We will be talking about using drop factors in our next presentation.